Good morning everybody. I am Dr. Khan. Today I am going to give you a demonstration on the experiment to draw the BH curve of ferromagnetic material using solenoid and to determine energy loss from hysteresis curve. And also I am going to discuss about the verification of Steinmetz law. And before I give the demonstration, let me briefly discuss what is hysteresis loop and how to calculate the hysteresis loss. Here we are considering the ferromagnetic material. As we all know that the ferromagnetic material has the domain structure. So the schematic diagram shows these are the domains and the local magnetic fields are directed along this direction in these domains. As there is random orientation of the magnetic moments, therefore the total magnetic moment is zero. As the local magnetic field direction is randomly oriented, the total magnetic moment becomes zero in the absence of external magnetic field. But when the sample is subjected to the external magnetic field, then the sample gets magnetized and we get the neat magnetization, and that magnetization is represented by the vector capital M like this. This is the magnetization vector, and the definition of magnetization M is the magnetic dipole moment per unit volume. And this is the hysteresis loop. And how we get the hysteresis loop? As I mentioned, we apply the external magnetic field H. So, if we take a sample and we measure the magnetization vector M and try to plot the MH curve, it goes like this. So H is increased along this direction from 0 here, and it can be taken towards the negative direction minus H also. So if we take the sample and increase the magnetic field, then the magnetization follows this curve. So it goes through A, through the point C, and reaches the saturation at the point C dash. So this is the highest or maximum magnetization. Now if we decrease the magnetic field towards 0, then what we find, this magnetization curve does not retrace. So it takes another path. So instead of coming towards 0 along this path, C dash C A 0, it takes this path, C dash C D. Therefore, the process is irreversible, as the magnetization does not retraces. An interesting phenomena is happening here. Here, when the external magnetic field is 0 at the point O, then magnetization, which is supposed to be getting the value 0, instead of getting value 0, it is getting the value D, OD. So it is not becoming 0. Magnetization is not becoming 0 when the magnetic field is 0. So this is called the residual or remanent magnetization. And this special property of the ferromagnetic material is called the retentivity. And now if we reverse the direction of the magnetic field like this, if we increase, then the magnetization comes down and it becomes 0 at the point E. So we have the magnetic field in the negative direction to make the magnetization 0. This is called coercivity, like this. And again, if we keep on increasing the magnetic field value in the opposite direction, then this magnetization takes the negative value and it goes towards F dash, where it again saturates. So this is the maximum value when the field is positive, and this is the maximum value of the magnetization when the field is directed oppositely. Now again, if we change the direction of the magnetic field like this, if we increase it, then what happens? It takes this route. So it goes from F, then to G, then to K, and then it reaches here. So the magnetization is not retracing the path, it's an irreversible process. And this loop is called the hysteresis loop. Instead of magnetization M, we can plot magnetic induction with respect to H. So this can be B field also, induction, magnetic induction also. And then the curve will be BH curve. And so this follows that if we go for a full cycle, then the magnetization won't be 0 with the 0 external magnetic field. So ferromagnetic material, once magnetized, cannot be demagnetized just taking it through a cycle of demagnetization. So this is the process of demagnetization. Once it is magnetized, we have to slowly reduce the magnitude of the external field, and it will take numerous cycles to make the M value 0 with the 0 external field. So this is called the demagnetization process. So what we find, due to this magnetization and demagnetization process, there is energy loss, and we have to calculate that energy loss first mathematically and then experimentally. And we find in brief the work done per unit volume for a cycle of magnetization. W is equal to mu 0 times the area enclosed by the hysteresis loop, that is MH loop or BH loop. And this relation W is equal to mu naught H dm or W is equal to H dB. The connection between them can be obtained from this relation. This is the relation among magnetic induction vector, external magnetic field and magnetization. So if we differentiate, we find dB is equal to mu naught dH plus dm, and this is 0. So H dB is equal to mu naught H dm. Thus the work done or the hysteresis loss or energy loss is related with the area of the hysteresis loop for MH loop or BH loop. So for our experiment, we have to get the hysteresis loop in the oscilloscope, and then we have to try to find the area of that loop. That is our main aim of this experiment. And the circuit diagram for the experiment to find the area of the hysteresis loop, as we mentioned in the title of the experiment, we have to use a solenoid, and that solenoid will be used with a ferromagnetic material, in this case iron rod, as a core of the solenoid, like this. And we have two sides, the primary sides and the secondary sides of the solenoid, and this primary side has the input AC signal and a variable resistance, and in the secondary side we have a RC network where both R and C can be varied. In this case, the input signal for the hysteresis loop is taken as the voltage drop across this R1 in the primary network, and that is taken as the X signal of the CRO. And this RC network is actually, this is an integrator circuit, and we take the output across the capacitor C, which is variable. My Y signal for the CRO is the voltage drop across the capacitor, and the X signal is the voltage drop across this R1. And then we have to take both X and Y in the CRO, and we have to take the display will be in the XY mode to get the hysteresis loop. Now let's do the experiment. Okay, this is my trainer board to get the BH loop or hysteresis loop in the oscilloscope. So this is my oscilloscope, and the circuit we have, this is a solenoid, and the core, I can take this iron stick, and in that case we have to insert it here like this, or we can use multiple sticks also, so like this, and we can insert here. So in both the cases we will have the hysteresis loop, and in these two cases the lengths are same, but the area of cross section will change. This is the solenoid. We have primary and secondary turns, and the primary circuit is here and the secondary circuit is here. This primary circuit has the R1, as I showed you in the whiteboard, that R1 is variable, so that can be varied to get the maximum and minimum current. And this voltage drop across R1 is taken through these two terminals. This green one is grounded, and X is the voltage across the R1 resistance. And this primary part is having the input AC signal from a transformer, that is 220 volt AC transformer, that is giving the voltage output that gives the primary current. And the secondary part is having an integrator, that is RC network. I have the R, which is variable, that can be varied with this pot, and the C, that also can be varied. I have three options in this trainer board, but we can have a band switch with more number of options. So to have the capacitor, I have to connect this one to this one, or this one, or this one. So depending upon the requirement, we can select different value of the capacitors. I have three numbers starting from 0.01 microfarad, 0.022 microfarad, and 0.047 microfarad. So I am keeping it fixed with 0.22 microfarad, and the voltage drop across the capacitor is the Y signal for my experiment. So So I have the CRO, I have X channel and Y channel. X channel signal is between this one and the ground, and the Y channel signal is between this terminal and the ground. So I am making them short, and these two signals are taken in the oscilloscope, and the channels are in the AC mode with the scale 1 volt in each channel, and I am displaying the signal in the XY mode. Now I have to switch on this. So I am keeping the iron core inside and switching it on. Now I have to adjust the scale. Let me see how it goes. So here, okay, what we find, this is our hysteresis loop, and we can adjust the input and output also. We can adjust output. Here I am changing the R2 value. Okay, so I am getting the different types of hysteresis loop, and I can also select different C value as I mentioned. So if I select some other C, then it is getting worse. Then if I change, it is also not good. I feel 0.022 microfarad is giving the best result here with the given input. Now if I change the input, the shape will change. So okay, so with this iron core, I mean the bunch of iron sticks I have taken, if I take single iron stick, then the loop is becoming thinner. So the area of the loop depends upon the dimension of the iron core. So you can play around with the input resistance, output resistance, capacitance value. That means the components of integrator. RC network, as I mentioned, so I can play with the value of R and C value. Now if I have this hysteresis loop, I can stop it like this. So it's frozen now. My assignment is to find the area of this hysteresis loop, because the area will give me the energy loss that I mentioned in the whiteboard. So to find the area, I can do two things. Here itself I can find the area, or I can take the image from this CRO to the computer, to a laptop or PC through this USB port. Data cable I can use to find the image in the computer. There I can process it, I can find the area. But simply to find the area, I have to make it symmetric with respect to origin. So here it is, okay, this I can move a little this way, horizontal movement will, okay, now the signal is about this point and about okay. So this is a kind of graph paper. So this grid structure is kind of a graph paper, and the area of each square is 1 centimeter square. So how many squares it is covering, that will give me the area of the hysteresis loop. So that is a standard procedure to find the area of the hysteresis loop with the graph paper, with the help of square of the graph paper. Okay, I hope you all have understood how to find the hysteresis loop in the oscilloscope using this simple circuit. So let's get back to the whiteboard once again. So back to the whiteboard once again. I have given you the demonstration how to obtain the hysteresis loop and how to calculate the area of the hysteresis loop. And it was like this. So we have the hysteresis loop like this, and we have to calculate the area under this curve. So for that we have to make use of the graph paper or the screen of the CRO. As we know, each small divisions on the screen of the CRO, it is 1 centimeter, so we can find how many square it is covering. So from that we can calculate the area of the hysteresis loop, and thus we can calculate the energy loss or hysteresis loss of the ferromagnetic material. And at the end I come to the point of Steinmetz law. That is a verification of Steinmetz law. Briefly, this Steinmetz law is the empirical law to calculate the order of magnitude of the hysteresis loss. And the law is the following. So the work done or the hysteresis loss W is equal to eta B max to the power n, where this n is generally taken for all samples 1.6. It's a constant, and eta is called the Steinmetz coefficient. It depends upon the sample or the substance used for the hysteresis loss experiment. And this B max is the maximum value of the magnetic induction vector obtained during the magnetization process. So this saturation value is the B max. This saturation value is the B max for the given sample. So knowing B max, eta, and putting n, we can calculate W. That gives the order of magnitude of hysteresis loss for a given sample. That has a lot of practical applications. So I have given you the demonstration to draw the BH curve of ferromagnetic material using solenoid and determine energy loss from hysteresis curve, and I discussed about the Steinmetz law. So I hope you all will be able to do the experiment in the laboratory, and students will be very happy. Thank you. Thank you for watching this video. Have a nice day.